Hello, everybody. Welcome to a brand new chapter in stats. Probably one of the last of the bigger ones that we have in multiple regression analysis. So something right along the lines. Sorry, already starting off with coughing. Of chapter 13, which went through a linear regression. So we're going to add an additional independent variables, and so on, till the end of time. That's basically what we're doing to help us better explain or predict a dependent variable. This is more general situations. Multiple regression analysis can be used as either a descriptive or inferential technique. So, you know the drill. Learning objectives. What are we supposed to learn in this chapter? Well, we're going to use multiple regression analysis to describe and interpret a relationship between several independent variables and dependent variables. We're going to evaluate how well a multiple regression equation fits the data. We're going to test the hypothesis, because we already know we're going to always test now, about the relationships inferred by a multiple regression model. We're going to evaluate the assumptions of multiple regression. We're going to use an interpretive of a quantitative dummy variable in multiple regression. Then we're going to apply stepwise regression to develop a multiple regression model and apply multiple regression techniques to develop a linear model. You already know this is going to be fun. So much fun. Don't worry about it. We got this, okay? I have faith. So, our multiple regression analysis has this kind of equation. Y hat equals A plus B1x1 plus B2x2 plus B3x3, so forth and so on till the end of time. That's why they have K. K can represent any number. So, value of various independent. Alright. So when there are two independent variables, the relationship can be graphically portrayed as a plane. So basically putting in the Z scale, almost a 3D plane going on. But yes, it's a fun little plane where observed points Y, estimate points of Y hat, all throws a little bit of fun. Now we're really going into the background multiple. So, we really cannot use a graph to illustrate more than two independent variables since graphs are limited to 3 dimensions. The chart shows the residual as the difference between the actual Y and the fitted on that plane. It's a lot, okay? This is going into deeper analysis. So the least squares criterion is used to develop the regression equation. So we're still using least squares from chapter 13. So supposing selling price of a home is directly related to the number of rooms and inversely related to its age. Let x1 refer to the number of rooms, x2 to the age of the home, and y hat to the selling price of the home. So it gives us this scenario. Y hat equals to 21.2, because again, that's the y-intercept, plus 18.7 x1 minus 0.25 x2. And then we can actually look up using any number that we like and find the selling price. So a 7-room house, according to this equation, that is 30 years old, is expected to sell for $144,600. Neat. Again, these slopes that we have, the 18.7 does indicate that for each increase of one room, the selling price will increase by 18,700, and the 0.25 indicates that for each increase of a year, the home will decrease in value of 250. So we can't have add and subtract. One's a negative. Alright, example time. Open the example and see what's inside. Sorry. Salisbury Realty sells homes along the east coast of the United States. One question frequently asked by the prospective buyers is, how much can we expect to pay to heat the homes in the winter? The research department of Salisbury thinks three variables relate to heating costs: the mean daily outside temperature, the number of inches of insulation, and the age and the years of the furnace. They conduct a random sample of 20 homes. Determine the regression analysis. So here we have three independent values. We have, again, the outside temperature, inches of insulation, and the age of the furnace. So, y hat will be the estimate of the value of basically RY, which is our dependent value of how much you're expected to pay to heat the home in the winter. They did a nice little graph. We like the little chart. Then they went ahead and put it in Excel right here. And this is that whole summary, that data analysis that we just discovered in chapter 13 to help us with regression with that chapter. Now we have it for multiple regression. That's where you see multiple R. So, here, once we determine the regression equation, we can calculate the heating cost for January, giving the mean outside temperature is 30 degrees. There are 5 inches of insulation in a furnace of 10 years old. Now, because multiple regression does usually have to take a little bit of statistical software to use, this is why the book has opted to go with Excel and that fun little data analysis. Notice here, here's our equation right here. See. Yeah. So here's our equation right here. Now, how did we find this? Well, the intercept is right here. So there's our intercept. And then look at the other coefficients. Negative 4.583. That is our temp slope. Negative 14.831 is right there in our insulation. And then positive 6.101 is right there with the age. I know, lots of arrows. But that's where they're getting the slopes at. So they're trying to help with the calculations by using the software that we have. Now, if I do put all the numbers into the formula, the 30 degrees, 5 inches, and 10 years, we come out to 276.56, which is the estimated heat cost of January as of that amount. And again, right here, since it's all in one page, you can probably put the formula right in here and have it calculated for yourself. We end up doing that with the practice problem. Now, ANOVA table. And yes, we actually have the ANOVA table right here. But again, ANOVA table summarizes the multiple regression analysis. It reports the total amount of variation divided in two components: the regression, the variation in all the independent variables, and the residual or error, the unexplained variation of y. We have our formulas right here, how it's calculated. It reports the degrees of freedom of the independent variables, the error variation, and the total variation. So again, that's what all this ANOVA is doing. Okay, so there's our sample standards error right here, SSE. So regression of sum of squares, and our residual error of sum of squares. Now, there are two measures of effectiveness of the regression equation. One is the multiple standard error of the estimate is similar to the standard deviation. Okay. It is measured in the same units as the dependent variable. It is based on the square deviations between the observed and the predicted values of the dependent variable. It ranges from 0 to plus infinity. Woo! To infinity and nowhere beyond. Anyway, it is calculated from the following equation. This is our nice equation that we have. But we can also use our regression. So here it is back again for us to figure out. Okay. So yes, they do have the formulas here showing this, and now we have 35 degrees temperature, 3 inches of insulation, and 6 years. Then y minus y hat squared is 250 minus 258.90 squared equals 8.90 squared. Alright, so basically they're finding the standard error right there. Okay, so what they're doing right here, okay, it's like, where's these numbers coming from? So again, we know the formula. So where they're getting the 35, 3, and 6, try and use the pen a little bit more this time around, and the 250, they're all pulling that from this line right here, okay? Because it actually has the temperature, insulation, and age. What they're doing is finding how much of an error between the two. Okay? Basically, what's the difference? Why is it not following the regression? Okay? That's one way of doing it. You could go through all these and we could find the average, so forth and so on. Or we could just do this formula. Okay, the multiple standard error of estimate. Where we take right here. Whoa, now I went right through on the line. But right, basically from the ANOVA, that line right there is the one that gets square root. Okay. So that's how we actually do this. Multiple standard error of estimate. Using our Excel to help us out, we pull it from right there. And we square root it, and we find out that $51.05 is the typical error that we can use this equation to predict the cost. So yes, it could be off just a little bit like that. Is it going to be perfect? No, these are estimates, but it will be close enough for our analysis. Next, measure of effectiveness, coefficient of multiple determination. Yes, we're still determined. So, percent of variation in the dependent variable y explained by the set of independent variables. Again, the coefficient of multiple determination is symbolized by r squared, capital R squared now, not lowercase like in chapter 13. Can range from 0 to 1, cannot assume negative values, is easy to interpret. It is found by the formula of r squared equals SSR divided by SS total. Again, we can actually use our table right here to figure this out. But it also has it, sorry, right here with r squared. That 0.804 is right there, 0.804. Okay, so there's an 80.4% of the variation is explained by the three independent variables. Now I can also pop my SSR, which is the 171, and divide it by the total. So what they did is they took this number and they divided by the total. Right there. Either way will work. But I mean, if it's already giving you the answer, there we go. That's the one good thing about statistical software. It does help us out, especially with the especially when the computations is starting to get a little bit more in depth. Again, we really just want to know how well can you interpret the data. So, when the number of independent variables is large, we adjust the coefficient of determination for degrees of freedom as follows. You take 1 minus SSE divided by n minus k plus 1 divided by the SS total divided by n minus 1. Okay. For the cost of heating example, the adjusted coefficient of determination, after we pull everything from our charts, equals to 0.767. If we compare it to r squared, to adjust r squared to 0.767, the difference in this case is small. We're not really seeing a lot of change. Again, also, boom, it also does the calculation in Excel. There's the 0.767. I know you are like going, yay, Excel! Woo! Alright. So, global test. A global test investigates whether it is possible that all the independent variables have zero regression coefficients. Basically, here's your hypothesis. Our beta 1 equals beta 2 equals beta 3 equals 0. Now all betas are 0. So they're not equal to 0. Test statistic is the F distribution. There is a family of S distributions. The F distribution cannot be negative. It is continuous, positive skewed, and asymptomatic. Subtonic. Now, sometimes I wish I could say the words correctly when I talk to y'all. But it does happen. So, guess what? We're still using the numbers. So, the formula to calculate the value of the test statistic is F equals SSR divided by K divided by SSE divided by n minus k plus 1, with k is the number of independent variables, degrees of freedom in the numerator. N minus k plus 1, degrees of freedom in the denominator. N is the sample size, which is 20 for this one. But we can obtain the degrees of freedom from the ANOVA table. What? Actually, we had 19, huh? They did say they pulled 20, but we're doing 19, I guess. It works. Either way is fine. So, there's our degrees of freedom. And we actually can pull pretty much mostly all of our numbers from here. Here's our F distribution. So, again, we're going to state the null in our alternative hypothesis. Our null, again, is everything that equals all the betas. Beta 1, beta 2, beta 3, all equal to 0. And not all betas are 0. Select the number level of significance. Most of the time, again, we're going to be using the 0.05, especially with the F statistic. Select the test statistic for F. Formulate the decision rule. Reject the null if F is greater than 3.24. Now, remember, we're going to use the chart found in Appendix B.6 to help us find this. And we get to use these numbers. So, 3 and 16. 3 is our numerator. I remember the top. And the denominator 16. That's on the side. Next, we're going to make a decision. Well, it already calculated our F statistic, which was 21.901. So, it's larger than 3.24. So, we would reject the null. So, step 6, interpret. At least one of the independent variables has the ability to explain the variation in heating cost. The global test assures us that outside temperature, the amount of insulation, or the age of the furnace has a bearing on heating cost. So we do know one of them does. So the test for individual variables determines which independent variable has regression coefficients that differ significantly from 0. The variables have a 0 regression coefficients are usually dropped from the analysis. The test statistic is the t distribution with n minus k plus 1 degrees of freedom. The formula to calculate the value of the test statistic for the individual test is as follows. T equals bi minus 0 divided by that error of bi. Okay. So, Salisbury Realty will use the 3 sets of hypotheses, one for the temperature, one for the insulation, and one for the age of the furnace. State the nulls. Okay. Beta 1 is going to equal 0. Beta 1 does not equal to 0. Notice that they're all this way. So that means they're all two-tail t-tests. Okay. Next, we're going to select the level of significance. We use 0.05. Select the test statistic. We'll use t. Now, we're going to formulate the decision rule. We're going to reject the null if t is less than or greater than 2.120. And we're going to make the decision. So, where do they pull all these numbers? The 0.0722, the 4.754, and the 4.012. Well, they're pulled from right here, the standard error. That's what goes into the denominator. These are the numbers that we're using in the numerator that we subtract 0 from. Which, it's just how it is. I really don't know why they're subtracting 0 when 0 doesn't really do anything, but it does affect. We do have two negatives there, but doesn't really affect. Mostly you're just dividing B2 by SB2. Alright, so we run the formula of each one, and then we compare. So we're going to reject the null for temperature and insulation, but not furnace age. Notice that these two are less than 2.120. But this one right here, the only positive number, is actually less than 2.120. So that means it falls in between, which we cannot reject it. So we can only reject 2, but the furnace age is not a significant predictor of heating cost. That's what we're interpreting here. So we know 2 are significant in temperature cost, which is installation and temperature, but not the furnace. So Salisbury Realty will rerun the regression equation using temperature and installation. The hypothesis and detail of the global test are reject the null hypothesis if F is greater than 3.59. Again, they're using Excel to find the degrees of freedom and everything from the ANOVA table. They're just summarizing it right here. Okay, and then they find F, which is 29.424, and for temperature, again, we find it negative 7.337 and negative 2.83. Okay, we did our calculations. Significant level was 0.05. Test statistic, we'll use T. Formulate the decision rule. Reject the null if T is less than negative 2.110 or greater than 2.110. And determine. Well, we're still rejecting for temperature installation. So both of them interpret they are significant predictors of heating cost. Woo! Okay. So yes, we can keep, as you can see, since one can be eliminated, we eliminated that to try and get even more specific to see what actually helps predict the item that we're looking for. It's what we have in multiple regression. So assumptions that we have. There are 5 assumptions to use. 1, there is a linear relationship. 2, the variation in the residual is the same for both large and small values of y hat. 3, the residual follows the normal distribution. 4, the independent variables should not be correlated. 5, the residuals are independent. Next, we'll provide a brief discussion of each of these assumptions. Why? Because why not? Why? Because why not? First off, the linear relationship assumption. The relationship between the dependent variables and the set of independent variables must be linear. To verify this assumption, we can develop a scatter diagram and plot the dependent variables on the vertical axis and the independent variables on the horizontal, just like we did in Chapter 13. Plots below indicate a fairly strong negative relationship between temperature and heating cost, and negative relationships between insulation and cost. Again, using our little table, we can actually see kind of going down. This one's a little bit trickier, but it is showing a downward path. Both of them have it. So, again, you can probably draw a line. It's not going to be the best line. But we both can see a little bit of a negative trend. So, to verify the linearity assumptions, we can plot the residuals to evaluate the linearity of the multiple regression line. The residuals are plotted on the vertical axis and are centered around 0 against the predictable value y hat on the horizon axis. Again, the plot on the left shows the residual plots for the home heating cost example. The plots are scattered, there is no obvious pattern, and there are both positive and negative values. Therefore, there is no reason to doubt the linearity assumption. The points in the plot on the right are non-random. This is not a random pattern, which shows the relationship is probably non-linear. I got a U-shape going on there. So our variation assumption, number 2. Variation is the same for both large and small values of y hat. This is known as homoscedasticity. I totally butchered that. Yeah, tongue twister there. Sorry, guys. Which is basically the variation around the regression equation is the same for all the values of the independent variables. Okay. This condition is checked by developing that scatter diagram with the residuals on the vertical axis and the fitted values on the horizontal axis. If there's not a pattern to the plots, that is, they appear random, the residual meets the homoscedasticity requirement. We did this on the previous slide, and based on the scatter diagram, it is reasonable to conclude that the assumption has been violated. So, we suspect that as age increases, so does income, but there is likely to be variation in incomes between 50-year-olds than there are for 35-year-olds. They went to a different... That is an interesting example. Next, the normal probability assumption. The residuals follow the normal probability distribution. The condition is checked by developing a histogram. Woo! Histogram coming all the way back from the first few chapters of the residual or normal probability plot. The mean of the distribution of the residuals is 0. If the plot points are fairly close to the straight line, draw from lower left to upper right, the normal probability assumption is supported. Again, they're graphing the 20 observations. Does appear normal assumption is reasonable for both the histogram and the normal probability plot. The normal probability plot is often included in statistical software. And mostly like Minitab. Alright. Evaluating multicollinearity. Big words. Multicollinearity exists when independent variables are correlated. For multiple regression analysis, we assume that the independent variables are not correlated. Okay? A correlation matrix will show all possible correlations among independent variables. A general rule is the correlation between two independent variables is between negative 0.7 and 7.7. There likely is not a problem. Signs of correlation in independent variables. An important predictive variable is found insignificant. An obvious reversal occurs in signs in one or more of the independent variables. A variable is removed from the solution. There is a large change in the regression coefficients. So, to figure this out, we use the VIF, the variance inflation factor. Yes. Which is 1 divided by 1 minus r squared j. Okay. So, again, we're going to be looking at this, and we're going to see that the problem is that may lead to erroneous results in the hypothesis test for the individual independent variable. If we do have this correlation going on, a VIF greater than 10 is considered unsatisfactory, indicating that the independent variable should be removed from the analysis. So here we go. So again, relating to the heating cost of the independent variables, outside temperature, amount of installation, and age of furnace. Develop a correlation matrix for all the independent variables. Does it appear that there is a problem with multicollinearity? Find and interpret the VIF for each of the independent variables. Now, because we are looking for correlation between, you're going to notice you do see this one step. Okay. So we do have the 1 point because we're doing temperature to temperature. But temperature to cost, you have all those, but this is the big one. Installation to temperature, age to temperature, and installation. Again, it basically defines all three. Notice that the correlation between negative 0.70 and 0.7 all works. We do not suspect problems with multicollinearity. Next, we do have r squared. Okay. So VIF 1 divided by 1 minus r squared 1 equals to 1.32. And they will have to go into multiple ones for each individual. And we do find it for 0.011 for our second one. And then 0.236 for the third, which of course is our furnace. So all VIFs do end up being less than 10, so there is no multicollinearity going on. Nice. Independent observation assumption. Each residual is independent of other residuals. Autocorrelation occurs when successful residuals are correlated. When autocorrelation exists, the value of the standard error will be biased and will return poor results for tests of hypothesis regarding the regression coefficients. Basically, this is what happens. Autocorrelation frequently occurs when data are collected over a period of time. A scatter plot, such as what we have right here, would indicate possible autocorrelation. This is a test for autocorrelation called the Durbin-Watson. Probably going to look at that Durbin-Watson in the next chapter. Not been removed from the book. But we'll look at it a little bit more in depth later on. Alright, techniques to build a regression model. Several techniques help build a regression model. First off, we have the dummy variable. A variable in which there are only two possible outcomes. For analysis, one of the outcomes is coded a 1 and the other is 0. A dummy or qualitative independent variable can assume one of the two possible outcomes, a 1 or a 0. Okay. Again, using our formula to determine that the dummy variable should remain in the equation. Example. So, So basically they're using the testing individual. I don't know why they didn't just say it. 14-6. Alright. Example, suppose we are interested in estimating an executive's salary on the basis of years of experience and whether he or she graduated college. Graduation will be a yes or no. So that's pretty much going to be probably our dummy variable. So again, since we only have yes or no, that could be 1 or 0. But here we go on this one. Suppose in the Salisbury Realty example that we've been using, that independent variable garage is added. So now we've jumped to a garage instead of the furnace. For homes without a garage, 0 is used. For homes with attached garage, 1 is used. Garage will be a variable of x4. What is the effective of the garage variable? Okay. So again, it puts all the information in. We calculate, and we suppose we have 2 houses exactly alike in Buffalo, New York. One has an attached garage and the other does not. Both have 3 inches of insulation and the temperature is 30 degrees. Okay. They're going to do all the calculations. Should the garage variable be included? That's what we want to figure out. Alright, again, with the calculations, we take our information that we pull from our table and we put in the numbers. Okay? So, we find out that without an attached garage, the heating cost is $280, while with an attached garage, the heating cost jumps up to $357. So now we can run our test to see if that actually works out. So, again, beta 4, since we're looking at the garage specifically, equals 0. And again, we're going to use the level of significance at 0.05. We're going to select T to statistic, formulate decision rule, reject H null if less than negative 2.120 or greater than 2.120. So once we do the test statistic, again, we pull the numbers from our chart. Right there, right down here at the bottom. In fact, it even has the t-stat. So, but we can always do the math. It all works out. So make the decision to reject the null. T equals 3.399. It is greater than 2.120. So we conclude that the regression coefficient is not 0 and the independent variable garage should be included in the analysis. Alright, last but not least, stepwise regression. Okay? This is a step-by-step method to determine a regression equation that begins with a single independent variable and adds or deletes independent variables one by one. Only independent variables with non-zero regression coefficients are included in the regression equation. Advantages to the stepwise method. Only independent variables with significant regression coefficients are entered. The steps involved in building the regression equation are clear. If it's efficient in finding the regression equation with only significant regression coefficients, the change in the multiple standard error of estimate and the coefficient of determination are shown. Okay. So here we go. Step-right procedure selects the independent variable temperature first. Temperature explains 65.85% of the variation in heating cost. Okay. The next independent variable selected is garage. Now the coefficient of determination is up to 80.46%. Okay. Next, the procedure selects the insulation and stops. At this point, 86.98% of the variation is explained. This is the same regression equation we just developed before. All it is a step-by-step. Step by step. Oh, baby. Do, 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 do. Again, if I want to look at the chart, we can also see with our regression squares that we are getting up into that 86.98, 0.87. So a little bit of rounding that ends up happening, but it does end up coming out to the same. And here is a stepwise technique. Continue. This is in Minitab. So fun, since we don't have access to the software. If you have to take a higher level stats course, you definitely want to have this. But we don't really have to deal with this in our we don't have access to Minitab, fortunately. But again, it just shows the same info as it explains more and more r squared higher up as we go. Alright, fun part now, the practice problems. Let's see what we got. Alright. So, a consulting group was hired by the Human Resource Department at General Mills, Inc. to survey company employees regarding their degree of satisfaction with their quality of life. A special index called the Index of Satisfaction was used to measure satisfaction. 6 factors were studied, namely age at the time of the first marriage, annual income, number of children living, value of all assets, the status of health in the form of an index. Wow. And the average number of social activities per week, such as bowling and dancing. Suppose the multiple regression equation is such and such. What is the estimate in the index of satisfaction for a person who is married at 18, has an annual income of $26,500, has 3 children living, has access to $156,000, has an index health status of 141, and has 2.5 social activities a week on the average. So basically all we're doing right here, and since they already calculated our formula, is fill in the blanks. So, get our fancy calculator. That's all we really need. So we have 16.24 plus 0.017 times 18, since that was our marriage, plus 0.0028 times 26,500, 42 times 3, whereas 3 children, add 0.0012 times 156,000 plus 0.19 times 141, and last 26.8 times 2.5. So we come out to 497.736 is his satisfaction index. How does they interpret that? That is up to them. Next, which would add more to satisfaction? An additional income of $10,000, a year, or 2 more social activities a week? So, basically, looking at our numbers here, even if I add 10,000, income added is only 0.0028 of our formula, but activities will actually be is 26.8. So if I take 26.8 times 2, that's 53.6. Well, I'm only getting like 28 points from here for that 10,000. Doesn't compute. So social activities went out on this. Add more social activities. All right. Question 5. Consider the ANOVA table that follows. Yes, we have our ANOVA table. They give us one. We don't have to actually go pop up in Excel. So, you ever think just randomly you want to say, I'm really good at it. I'm really good at it. Anyway. You're probably going, no. Just do it. Alright, so determine the standard error of estimate. About 95% of the residuals will be between what two values? Alright. So, for us, the residual error, we can go through the whole formula, but remember, this right here is when we want to determine the standard error of estimate. We take that number and we're going to give it a good old square root. That was a bad square root, but really that's all we need to do. So let's take our calculator and go 9.414 and the square root of that. So we come out to about 3.068. So when we look at 0.95, now this is the fun part. This is based on the empirical rule. So basically, we take whatever the standard error is, since 0.95 actually represents 2. And remember, 0.99 is 3, so forth. So again, back to the empirical rule, which again we mostly use 0.95. We're going to take this 3.068 and times it by 2. So it comes to 6136, and this is going to be positive or negative since we're dealing with the two-tail. Okay. So B, determine the coefficient of multiple determination interpreting this value. Okay, so since we don't have the complete regression model that we would, just a ANOVA, we have to do a little bit more math. That's okay. That's how we learn. So remember, R squared is SSR, which is this one, divided by the total, SS total. So, for us to find R squared, we're going to take 77.907 and divide by 661.6, and R squared is about 11.8%. Again, long decimal, we just cut it off and round. Alright. Next, determine the coefficient of multiple determination adjusted for the degrees of freedom. Alright. So again, we don't have R squared adjusted. So we got to use the formula. And that formula was a little bit big because it was 1 minus our SSE, which is, I wish they gave me a different color. Let's see, ink color. Let's go with green. All right, so to do the residual, first we gotta look at the residual error to find this coefficient of multiple ones with adjusted degrees of freedom. So basically R squared adjusted. We take SSE, which is 583.9693, divided by N, which N, since this is a sample, is 65. So 64 plus 1 will equal to 65. Okay. Yeah, fun sample size. So N minus 2, that's what we got, numerator, plus 1 divided by our total. So we're going to use the total again, all in green, divided by N minus 1, which basically turns into 64. Okay? So, putting this in the calculator, now everybody's like going, yes, we like if it does statistics, it does the whole table. So, well, clear, 1 minus 583.693 divided by 65 minus 2 plus 1 then divided by 661.6 divided by 65 minus, minus 1. Oop, I probably forgot a parentheses there. Sorry about that. So let's try and do it. 0.693 divided by 65 minus 2 plus 1, close, close. So that's 9.414. Getting a little bit of rounding. 661.6 divided by 64 is 10.3775. So 9.414 divided by 10.3375 equals to about 0.911. 1 minus 0.911 is where we get a 0.089. So big complicated formula. Again, if we're able to use the complete regression model, again, it does the math for us, but again, you do have to know how to figure out the formula if it just gives you a ANOVA table. Makes it a lot more complicated than it should be. Alright. Last slide. Last practice problem. That's everything for chapter 14. Given the following regression model, okay, answer the following questions. Write the regression equation. So, our regression equation is y hat equals Again, our constant, 84. Wish they allowed me to type in, but 0.998. Alright. Next, our x1 plus 2.391 x times x1, and then the next one's a negative, so minus 0.409 x2. And I ran out of space. Sorry, guys. But basically, that is our item there. Alright. So that's our regression equation. If x1 is 4 and x2 is 11, what is the expected or predicted value of the dependent variable? Okay. So calculator. So we have 84.998 plus 2.391 times 4 minus 0.409 times 11 will equal about 90.063. Okay. How large is the sample? Okay. So, even though we have total, remember, since this is a sample size, add 1. So we have 65. Okay. So, 65 is in. How many independent variables are there? There's 2. We can actually see that with the degrees of freedom. It's really all that they're asking for. Okay. D. Conduct a global test of the hypothesis test. See if this set of regression coefficients will be different from 0. Use a 0.05 significant level. What is your conclusion? Alright, so our biggest thing that we have to figure out, one, if you're doing the null and the alternative, basically the null is again beta 1 equals beta 2 equals 0. The alternative is they don't all equal 0. So first thing that we have to do is figure out our F test. We have the number here. That's the calculation. But we need our book. So to the book, to the book, to the book. And here's our F distribution. Again, they're going to use 0.5 a lot since that's our table. And remember, our degrees of freedom here, 2 and 62. That's our numbers. So we're going to use 2, and we're going to find 62, which, because of how big it is, basically it's close enough to 60. That's where our chart ends. Again, there's not a significant value beyond that till we hit 120. So it ends up being 3.15. So, right there, we already know if F is 3.15, this is greater than, so 4.138. Our conclusion is to reject the null. Not all regression coefficients are equal to 0. Alright. Next, we're going to conduct a test hypothesis for each independent variable using the 0.05 significant level. Which variable would you consider eliminating? Okay, so first thing that we need to do, we do have our t values right here. 1.99 and negative 2.38. Again, tables already conducted that. That's nice. We just got to figure out what is the actual or critical value. So, next to the book. So, we are looking at, again, the 0.05. And since we're doing a equal, so because it has to equal to 0 and not equal, that means we're on a two-tailed test. So we're pretty much looking right here. Okay, next we go find our number. Should be 63. We have two variables. So we got 0.1998, 0.05, and we should actually end up with one where we actually keep this variable x2 because that is less. This is actually equals to 1.998. So this one is actually eliminated. It's within the barriers or equals. So that's a very close call there. But we will remove variable 1 and keep variable 2 because that actually is less than negative 2.0 or negative 1.99. I rounded there. Sorry. So, outline the strategy for deleting independent variables in this case. Well, the regression analysis should be repeated with only variable 2 as the independent variable. Okay, so that concludes chapter 14. A little bit of fun right there at the end. But again, as we saw, the regression analysis that we did in chapter 13, using that data analysis that's now in your Excel, actually gives us most of the information when we actually look at the information, or the data set. But it is safe to go ahead and remember the calculations. But using the ANOVA table will help you out. As you can see, using this table right here, it already calculated our T statistic and our F statistic. All we had to do was find out the critical value. Okay? If you have any questions, you know what to do. Let me know. And I will see you for the next lecture video, which is the last lecture video.